No one communicated.
All right. Come on, guys. This is our last day. We've only had 3 days of school this week.
Exactly. We're going to forget all of this over the
Our
weekend.
minds are...
We're burnt out. We're fried.
Okay, well, you guys have a day off tomorrow, so we gotta
Yeah, so we're going to forget all of this, this lesson.
And this is a really important lesson. I swear you guys are going to like this. It's one of those times in math where it's like, we've been making you do things the long way. Here's a shortcut.
Okay.
You know those times in math?
Can we it's going to...
I know,
it's going to make our Monday better.
Okay. Do you guys remember how to find limits?
No.
See, this is why we need a month of review. And this is why we have to do a lesson today.
I can remember limits. I don't remember infinity, though.
Okay, well, you always start by, like, plugging it in, right? And here, when you have infinity, if you were to, like, essentially plug in infinity, we have infinity over infinity. And you're like, we call that's kind of essentially an indeterminate form. Do you guys remember our strategy for what we do when we have limits as x approaches infinity?
So?
Yes.
On the left and right? I know.
No, but I like thinking. That is if... Ooh, I just got shocked by the board.
That's telling you we shouldn't be doing this. That's very fine.
We looked at the left and right if we get something like this where we think there's an asymptote, if we get like some number over 0. Okay, good guess, but that is a limit strategy. Do you remember?
No.
Tails? People call you that? People call me that.
Yeah.
Oh, Rachel.
That's my mom's name.
We'll call you your mom's name. So you like it.
Call me Dana if you want.
Mark, come on.
You factor?
Mark is super excited today. He's like ready to learn. Eager.
She heard me complaining.
All right. Wait, Mark, do you remember? Before I give a hint.
Actually, factor.
Okay, factoring is a strategy, but not in this case.
You gotta get rid of the denominator.
Okay, it is something with the denominator. We divide by the
Lowest.
largest
Power.
in the denominator. We divide everything by the largest power in the denominator. So in this case, my largest power in the denominator is x squared. So I technically would divide everything by x squared. And how you kind of show your work is like this. Okay, remember this? Good times.
How about we just do one more problem today and then call it quits?
Oh my gosh, I didn't know you guys were so lazy.
It's not lazy.
I don't-
Out.
Laziness is something you can control.
This isn't laziness.
You're starting to sound like my pre-calc kids.
No, we're not that bad.
They're very whiny.
Where do you think they learned it from?
And I always brag about how great you guys are.
We are great.
That's why we need a break.
Okay. So I would divide everything by x squared. So up top, this would just end up being 3. Same with this one on bottom. This would end up being a 5x. So we kind of get to here, where we have 5x plus 3 plus 1 over x squared all over 3 plus 2 over x. These would cancel too. Okay, so that's kind of our strategy for limits as x approaches infinity, positive or negative infinity, because then you go ahead and basically like plug in a really, really large value. So if I were to plug in infinity, and you can like actually do it like this if this helps you visualize it, but then I'm going to have 3. Do you guys remember as if we have 1 divided by a really, really large number, what that ends up being close to? 0. Good. Yep. 1 over really large. It's going to get really, really close to 0. All over 3 plus, same with that 2 over x, would be 0. So up top we have 5 times something really, 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 really large, plus 3 plus 9, I think. So this is that. Obviously the numerator is just going to get really, really large. This one's going to go off to infinity. So that kind of tells you like your end behavior for that curve as x approaches infinity. So going this way, so does my graph. That's what we just found. Okay. So what I'm going to teach you today is there's an easier way to find that limit. It's going to be fun.
The limit on everything or?
On all limits?
Yeah.
Only ones that are in indeterminate form. So only ones that like when you plug it in, you get something like infinity over infinity, or this one when you plug in 0, because that's always our first thing to test is like, can I just direct substitute? So if I get this, what I've taught you thus far is that means there's like some more algebra that can be applied. And remember to always like cross that off your paper because you don't want the AP exam grader to think that you think 0 over 0 exists. So only when they're in this form we can use this new rule. Okay, so then our strategy for here is we would try to do like some sort of like algebra, and you're like, well, there's no like factoring, there's no radicals, there's nothing we can really do to simplify here. We could try the squeeze theorem. Okay, you probably don't remember what that is, so let's review over that. The squeeze theorem is like, we know the sine curve is bounded in between -1 and 1, if you think of what it looks like on a graph. So this is the squeeze theorem. You'll notice, though, the squeeze theorem doesn't work here. I don't know how to spell squeeze. Is it E? Is there not a U here? No. SQ. There is a U?
There's gotta be.
Yes, there is. Okay, squeeze theorem. I'm really bad at spelling. Is that what you guys are talking about? You have like spelling words?
Jason needs to send me the spelling.
I already did.
Did you?
Yep.
Oh, you're the best,
Aw.
Jason. I'll get you a pack of gum. Maybe.
Okay, so we've done a couple like this squeeze theorem with these limits. So basically what we try and do is we know the sine curve is bounded between -1 and 1 because it looks something like this. It's bounded between -1 and 1. So what we do is we try to manipulate the middle to look like this function here. So I would want to divide everything by x cubed. Now this already is kind of an issue because technically in math you should never really divide by variables because we don't know if the variable is 0. So technically this is like kind of mathematically illegal to divide by 0, but this is just to show you that if you were to try this squeeze theorem, it's not going to hold. So then we get the middle piece to look exactly like what we're trying to take the limit of. So then we take the limit of all of these, of this like compound inequality. Okay. So if we were to do that, the squeeze theorem here, we see here that I end up getting -1 over 0, which usually means there's a vertical asymptote. But again, there's no like simplifying I can do there. I only have that like 1 over x cubed. And if I were to do it over here, I'd get 1 over 0, which indicates, again, there's a vertical asymptote. So this one, the squeeze theorem, doesn't really work. So what I'm going to show you and introduce you today is another way we can evaluate these indeterminate form limits, and it's a lot easier. We'll actually come back to this problem later on and finish it. I'll show you how to do it using this new rule. Okay, so here's basically what you would have tried up until today, this exciting day, February 24th of your calculus career, where you guys get to learn something called, are you ready for this? Dun, 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 dun.
Hospital.
L'Hôpital's rule. L hospital? That was so funny. L'Hôpital's rule. That's how you pronounce it. L'Hôpital.
It's the hospital.
That's definitely not what I read at first.
Oh my gosh. Okay.
Thinking like Johns Hopkins Hospital.
Oh, that's hilarious. So the reason why we haven't taught you this yet is because it involves derivatives. So in chapter 1, when we were just doing limits, and limits, you need to know limits in order to understand what a derivative is. So now we can revisit using derivatives to help us with limits. So let's review over what the indeterminate form is. Remember, whenever I'm evaluating a limit, my first step is to direct substitute, and if I get something that's 0 over 0, we call that indeterminate form. when both my numerator, f of x and g of x, at whatever a is, when they're both 0, we call that indeterminate form. And obviously we can't find it by direct substituting in. So then what we've done before is there's always been some type of algebraic technique, factoring, rationalizing, that's allowed us to simplify it a little bit, and then we could eventually direct substitute. So basically 0 over 0, we call that indeterminate form, and it's just a meaningless expression, but indeterminate form. This is how it most commonly comes up, is 0 over 0, but there is another case of indeterminate form. We'll talk about that on the next slide. Okay. So one important thing about this that you need to think about right away is L'Hopital's rule only works when we direct substitute and we get the indeterminate form. If we get something like this, 1 over 0, that usually means our vertical asymptote, so then we have to look for the left, like just to the left and just to the right. Okay. So here's the general form of L'Hopital's rule. So suppose we get that indeterminate form that when I direct substitute a into both my numerator and my denominator, I get that 0 over 0. What you can do, this is L'Hopital's rule, is take the derivative of the top and the derivative of the bottom and then see if you can direct substitute in. Now, it's not quotient rule. It's not quotient rule. It's not like we're taking the derivative of this function that's like within the limit. You just literally take the derivative of the top and the derivative of the bottom. And then if you can direct substitute in, which a lot of the times you can, L'Hopital's rule says that that would be the same as evaluating the limit, is evaluating what the slopes are doing. Okay, now here's the big thing. L'Hopital's rule can also be applied if you get the indeterminate form like infinity over infinity, negative infinity over negative infinity, but your limit has to be in one of those forms in order to apply L'Hopital's rule. Important. Important. What if L'Hopital is a person? I know, you know the Riemann sums? That's named after a guy. His name's Bernard Riemann, who discovered them.
It'd be like something like French or something. Or
L'Hopital? Yeah, it does sound French, doesn't it? I was going to try to say important with a French accent, but I didn't know. Importante. I took French in high school.
Isn't that Spanish?
See, I can't.
No, Spanish is importante.
No, that's
Pretty much what I
That's
said.
what she said.
I recently was in an Uber with a driver who spoke French, and we actually had like a conversation a little bit in French. I like kind of could conversate with him just a little. Okay, so obviously for limits we always try to direct substitute first, but now if you get one of these two forms, you can just take the derivative and try that instead of having to factor or doing all these like squeeze theorem. I mean, squeeze theorem you might still need to use sometimes. I shouldn't rule that one out, but it's a lot easier than a lot of our algebra techniques. So these first couple problems, we're going to do it how we used to, and then the new way, and see how we get the same answer. It's going to be fun.
So is this the old one?
So it says evaluate the limit A using techniques from chapters 1 and 3, the old way, and then B using L'Hopital's rule. So we're going to do both for this one. Okay. So no matter if we were doing the old way or the new way, we would still try and direct substitute 1 in first. So I kind of show my work out to the side like this. I show plugging in 1. And remember, I put like the arrow like leads to, not equals to. And I see up top, that's obviously going to give me 0. And on bottom, I get 0. So I have this indeterminate form. Make sure you cross that off. Get in the habit of doing that. So if we were doing this in chapter 1, way back when, we would try to apply some algebra. And looking here, it looks like my top is factorable. So I'd probably try that. I'd factor out a 2. And then I see a difference of squares. So now I would factor that. Ah, feels good to review. Those cancel. And then we could direct substitute in, and we get -4. That one was a pretty simple one. Obviously, they can be a little bit more complicated with factoring, but that's a nice, easy example of algebra techniques to find that limit, which is fine. Using L'Hopital's rule, put that one in green. L'Hopital's rule says as long as you get the indeterminate form when you direct substitute, which we did, you can take the derivative of the top piece. Again, we're not doing quotient rule. You just literally take the derivative of the top, which is 4x. Oh my gosh. 4x. And then to take the derivative of the bottom, which is just 1. And then you can direct substitute, which that's obviously just 4x. So then we can substitute in -1. And we get -4. It works. Cool, huh? Wasn't that way easier?
Strange how well that worked.
Right? I remember one of my students last year was like, are you serious? We've been doing these limits a long way because we do it like way at the end in our old textbook. She's like, are you serious? You made us do it this way for like 7 months and there's an easier way to do it. I was like, yeah, but you need to know limits to understand derivatives, and now I can use derivatives to help us with limits. It's just all one big circle of life.
Circle of math.
Circle of calculus.
It's the geometry of math. Ironic.
Okay, let's try another one. So here, when I plug in 6, I get the square root of 16, which is 4 minus 4. Ooh, another indeterminate form. Ooh, don't put equals, put leads to. Leads to. So old us would have used some algebra techniques. Do you guys remember the strategy when we have radicals?
Multiplied by
Yep.
I don't remember the name.
Starts with a C.
Conjugate.
Conjugate. Good. Multiply by the conjugate. Even though the radical's in the numerator, it's not like we're trying to rationalize here. Multiplying by the conjugate can often simplify this for us. So the conjugate would be the exact same terms. So the root x plus 10 and the 4, but you do plus instead of minus. So conjugates have a nice way of multiplying out. Because when I distribute here, you get square root of x plus 10 times the square root of x plus 10, which is x plus 10. And you get plus 4, minus 4. Those outers and inners cancel, so you can just multiply first and just multiply last. You guys know that. And then I kind of showed you, don't ever really multiply through unless it's the conjugate, because usually you'd have to refactor it anyway. So I would keep the denominator just like that. And then we notice in my numerator there I have x minus 6. And then these end up canceling. And then I can direct substitute from there. And I would get, let's see, 1/8. 1/8. That's not wrong to do it that way. L'Hopital's rule is normally just a little quicker, unless obviously the directions tell you to use L'Hopital's rule. Okay, let's try L'Hopital's rule on this one. All right, so I just take the derivative of the top piece, which that would be x plus 10 to the 1/2 power. So I'd bring the power in front. X plus 10, drop 1, chain rule, derivative inside is just 1, the minus 4 is 0. all over, and then just take the derivative of the bottom, 1. All right, cleaning that up a little bit. Obviously, that over 1 is itself, so I'm going to move the 2 in the square root of x plus 10 to the bottom. And then I can try to direct substitute in there. And I get 1/8. Nice. Okay, so there's a nice little proof. I guess not really proof, but that L'Hopital's rule works. Finding limits the old way, using the new way, and we get the same answer. Okay, so let's just practice some using L'Hopital's rule now. We just have 8 problems to do, and then that's it.
I think it's dinner meal time. We're done.
And now, see, now that we know all these like derivative rules, like, now we can use L'Hopital's. We didn't know that before.
Can we do a Kahoot on L'Hopital?
You want to make it?
I'm sure there's one out there.
All right. So first step, direct substitute. My numerator, I get 0. What's the natural log of 1?
0.
0. So I do have that indeterminate form, meaning L'Hopital's rule can be applied. All right. Derivative of the top, 2x plus 2. My marker is not doing so hot today. It's just the green one. Okay, what's the derivative of the bottom?
1 over x.
1 over x. Nice. That's one of our new derivative rules. So instead of dividing by 1 over x, I'd probably times the top by the reciprocal. Or I guess you could really plug in 1 right away if you wanted to. I just like to simplify it a little bit first. Then do my substitution. We get 4. So that's a really good example of one. Obviously, now if I'm throwing in like natural log and e to the x's, you're like, so I still try to factor the top. How's that going to cancel out with something? And you would like have to use L'Hopital's rule. Now, technically, number 2 factors. First, we should direct substitute still. Which anything to the 0 is 1 minus 1. I do get that indeterminate form. Now, the top I could factor as a difference of squares, but honestly, let's just use L'Hopital's. Okay. Derivative of the top. Okay, e to the 2x is e to the 2x. Chain rule times 2. I'm going to put that 2 in front. Obviously, minus 1, 0. Derivative of the bottom is just e to the x. Now I can go ahead and direct substitute. You could we simplify this? We could. Let's do that, actually. We could subtract the powers. 2x minus 1x would just be that. Then you could direct substitute. You get 2. I don't know why I didn't think of that the first time to simplify first. See, not bad. 2 down.
We're out of time.
We probably
6
could
to
use,
go.
We probably could use these for Monday to make sure we remember everything.
Yeah.
Don't worry, I'll put some warm-up problems on the new packet.
What are you gonna say?
This was one from the warm-up.
I think we're gonna have to do that.
This one from the warm-up, and you guys didn't remember how to do it. So now let's see if we can use L'Hopital's. So again, when I plug in infinity, I get like a really large over a really large. So that's actually that other form of indeterminate form in which L'Hopital's rule can be applied. If you get infinity over infinity. So even though it's not that 0 over 0, that indeterminate form, L'Hopital's can apply for this as well. Make sure you still cross that off because technically that doesn't exist. Okay, so L'Hopital's. Take the derivative of the top, 15x squared. Oh, I just love polynomials. Over 6x. Derivative of the bottom, 6x plus 2. And then you notice here, okay, now I go to direct substitute and I still have an indeterminate form.
Derivative again.
What'd you say?
Derivative again.
Yes, you can do it twice. Let's derive it again. L'Hopital's rule times 2. Nice, Mark.
So smart.
See, imagine if we would have taken the day off. You wouldn't have said that.
I wouldn't.
Okay. Here, obviously, we could simplify this as 5x plus 1. And then when I go to plug in infinity, I obviously have 5 times infinity plus 1, so that's just going to go off to infinity. And if you remember from the warm-up, that is what we got when we did our technique of dividing by the largest power of x in the denominator. Oh, also, I should remind you, remember if this was like a multiple choice type of situation, this could technically be classified as does not exist. So it would never have one option infinity and another option does not exist. It'd have one or the other. So it could say infinity or it could say does not exist. And the reason why, if you remember this, is because technically the limit is defined as like a number, and technically infinity is not like a finite number. So some textbooks classified as does not exist, some will still classify it as infinity. So it shows up both ways on the AP exam. Okay, another one. Direct substitute. All right, cosine of 0 is 1 minus 1. I get 0 in the numerator. E to the 0 is 1 minus 0 minus 1. Indeterminate form. L'Hopital's can be applied. Oh, thank you. Don't put the equal sign. Put leads to. Good catch. I always do that. Okay. Let's do the derivative of the top. Negative sine of x. Bottom, e to the x is just e to the x minus 1 from that negative x. Direct substitute, and I'm like, ooh, I know the sine of 0 is 0. I know e to the 0 is 1. So again, another indeterminate form. L'Hopital's again. So that minus 1 will drop out. And now we can go ahead and direct substitute because I know my denominator is going to be 1. My numerator is going to be negative 1. That one's negative 1. Okay, we're halfway done. We only have 4 more to go. Don't worry, we got plenty of time. Okay, next one. Ooh. E to the x over x to the 4th. Now, if you think about plugging in infinity, obviously exponential growth is faster than polynomial growth. So you might be thinking, well, I have like a larger infinity over a smaller infinity. So it's probably just infinity. And that thinking is actually not wrong. Like you can, with these ones as x approaches positive or negative infinity, you can kind of think of it in ways like which one's going to dominate, which one's going to actually grow faster. But you can also use L'Hopital's because we do have that indeterminate form. So you can take the derivative of the top, which is just e to the x, the bottom, 4x cubed, and you probably know what this is leading to. You're like, okay, we still have that indeterminate form. So let's do L'Hopital's again. The numerator is just going to stay e to the x. And then I have 12x squared. You're like, still indeterminate form. I'm still going to get that infinity over infinity. So yes, you can do L'Hopital's a third time. You can do it as many times as you need to. You're like, oh, we're almost there. I still have an x in the denominator, so I'm still going to have this indeterminate form, even though I know my numerator is really dominating at this point. Like exponential growth compared to linear growth is going to be way faster. So we're already thinking we're probably going to go off to infinity, but let's keep going here with L'Hopital's. So I get e to the x over 24. And then you're like, okay, I have e to the infinity over 24. So that's just going to go off to infinity, something really large. Or again, technically that could be does not exist. Okay, I like that example because you can do L'Hopital's. How many times do you do it? 1, 2, 3, 4 times? Let's revisit the one from the warm-up. Now, this is the other one from the warm-up when we kind of tried to use squeeze theorem when we got stuck and we're like, I don't really know where to go from here. It looks like there might be some asymptotes if we use that squeeze theorem. Let's try using L'Hopital's because you'll notice when I do, which we did in the warm-up, when I do direct substitute, I get that indeterminate form. Okay. L'Hopital's, derivative of the top, derivative of the bottom. Now watch what happens here when I direct substitute 0. I don't get the indeterminate form because the cosine of 0 is 1. I get 1 over 0. So these are the ones that indicate we probably have a vertical asymptote. When you get a number over 0, probably have a vertical asymptote. So what we need to do is look at the limit as x approaches 0 from the left and 0 from the right and see if it's going off to positive or negative infinity. Okay. So I'll do it from the left first. So that'd be like negative 0.0001. And I'm using this one because that's the one where I got that 1 over 0 form, not the original. The original is that indeterminate form. Okay, so obviously up top we got 1 because the cosine of 0 is 1. So on bottom, if I have negative 0.00001 and I square that, times it by 3, I'm going to have a really small positive value, a positive tiny. And 1 divided by something really, really small that's positive would go off to infinity. So you're like, okay, that makes sense. It looks like we probably do have an asymptote here, but let's check the limit as x approaches 0 from the right. So it'd be like 0, 0, 0, 1. And because we have that x squared in the denominator, you're like, okay, it's going to be the same thing. It's going to be over a positive tiny. So technically this limit, so it's going to be doing something like this. As x approaches 0 from the left, up to infinity, 0 from the right, up to infinity. So again, there's probably an asymptote here. So again, these derivatives can be, or not derivatives, sorry. These limits can be classified 2 ways. Because they're both going in the same direction, it could say this limit is going off to infinity, or it doesn't exist. Either of those answers. Oh, this is going to be perfect timing, guys. We'll finish this right up.
I think it's time to call it quits.
What? We only have 2 left now.
We
Yeah,
might
warm
as
up on
well
Monday.
rip the rest of the Band-Aid off.
I got to figure out what we're doing Monday. We only have 2 more lessons of chapter 5. And then this is the last lesson before our next quiz. So I'll figure out what we're doing.
Quiz Monday. Just kidding. Just kidding.
All right. Now this one looks kind of weird because you're like, if I plug in infinity, I get the square root of infinity here. And then I get e to the negative infinity, which is like e over, or e to the infinity like in the denominator. So here, a better way to maybe like rearrange this for you guys to visualize this is I could technically use my negative exponent property, move that to the bottom. and then become e to the positive x. And then when I go to direct substitute in infinity, I'm not even going to put underneath the square root. Again, the bottom exponential growth is way larger than square root growth. So we probably think we're going to get 0 here because our denominator is bigger. But if I have this indeterminate form, I can use L'Hopital's to just make sure that my thinking is correct here. So let's go ahead and take the derivative of the square root of x, which is 1/2 x and negative 1/2. And then the bottom is just e to the x. So cleaning up my numerator. Do you guys have like this square root of x1 like almost like memorized now that it's just like 1/2 to the root x? Like that's the derivative. I feel like we do those so much that I could, or you could honestly jump from here to here if you wanted to. E to the x. And then when we go to direct substitute, I say, okay, I have 1/2. And again, you can plug in infinity if you want, but we're just going to have something really, really large. And it doesn't matter if it's positive or negative large. Do you guys remember that's what that's going to always equal?
0.
0. Yep. And again, if you ever forget those, do it in your calculator. Take 1 divided by something really, really, really large. You're going to get a really, really, really small number really, really close to 0. Okay. So again, you can almost tell that with these x approach infinity limits. Think of like, which one's going to grow faster? Which one's going to kind of dominate? And in this case, it was that e to the x. So if I have, something large over something way larger, it's still going to kind of go off to 0. But again, when in doubt, use L'Hopital's. Woo! I like this one. Okay. Here when I plug in infinity in for x, basically, you have infinity in your denominator, and a picture of this 1 to infinity, that definite integral that's also going to go out to infinity. So technically, we do have an indeterminate form here. I put this one in because you guys stink at finding derivatives of this, and it's really easy.
Isn't that already just plugging in x?
Yes, exactly. I feel like so many people got this problem wrong on the test. So to take the derivative of a definite integral, remember they're inverse operations. So essentially, the derivative just undoes the integral. And you can plug in this variable in for t. And then you do have to do chain rule. But the derivative of x is just 1. And this is the fundamental theorem of calculus. And just remember, technically, this bottom number has to be a constant in order for that to work. And it will be for you guys. They wouldn't give you one that didn't. So the derivative essentially undoes the integral. So you don't have to worry about that dt because they're inverse operations of each other. And then the bottom, the derivative of x is just 1. So then I have the natural log of e to the 4x minus 1. Those undo each other. So I really just have 4x minus 1. Substitute in infinity. So it's going to go out to infinity, or it does not exist. Okay. See, that's kind of a fun one, huh? Pretty easy rule, and it's a good review over a lot of these situations with limits. Okay, so let's talk about when we want to do the quiz.
Never. You can do a group quiz.
How about
The 3rd.
How about this? How about Workday Monday?
You couldn't just have that today.
Well, I want to. Now you can finish and work on the homework before the quiz. We've learned all the material that's gonna be on the quiz.
Mm-hmm.
Workday Monday. We'll start 5.7. We'll quiz Wednesday and do 5.8. I think 5.7 and 5.8 will either be 1 or 2 days, or 1 day lessons. Also, they're really short. So I'll do 5.7 quiz, 5.8 review. I'm gonna do another take-home quiz for 5.7, 5.8, and then we'll maybe test somewhere. I don't know. We'll see how it goes. So let's put on a quiz next Wednesday. I think that would work.
So Monday we have work, and Tuesday we start new notes.
Yeah, Tuesday we'll start 5.7 just to give you more time to kind of get your homework done. Wednesday we'll quiz over 5.4, 5.6, 5. No, 5.4, 5.5, 5.6. Yeah, those 3. 5.4, 5.5, 5.6. When's the end of the quarter?
No
When's spring break? This week?
Yeah.
Yeah, so if we got the chapter 5 test in, yeah, we're not going to finish chapter 6, and that's okay.
Isn't there 7 chapters?
Yes, but we don't do all of chapter 7. And chapter 6, I think, is only like 4 sections. I gotta look. I was thinking about just combining them.